In semiconductors, there exists diffusion currents along with drift currents. In conductors, only drift currents exist. Diffusion currents are absent in them. Now, a few words, a few points describing diffusion currents. Currents that result due to diffusion phenomena. They are called diffusion currents. Diffusion phenomena is a natural phenomenon. It refers to movement of particles from more concentrated regions to lesser concentrated regions. This phenomena doesn't require, it doesn't involve any agency for moving the particles, like potential gradient in case of drift currents. This is natural phenomena. Nature itself moves the particles. Another aspect, important aspect to be kept in mind regarding diffusion is it is not specific to charged particles. Diffusion exists even in gases. Gases molecules also undergo diffusion. This is in contrast to the phenomena drift, which is associated with charged particles. Drift is not associated with gaseous molecules. In semiconductors, we come across several situations where electrons are injected from one end, holes are injected from one end. The injected electrons, the injected holes, then they tend to move to the other end. It is a natural process. This process is diffusion. As a result of diffusion, one can notice particles move, leading to the generation of current. Of course, it consists of usually two components, one due to electrons, another due to holes. Now, a parameter, it is called diffusion constant. This parameter is used to describe the diffusion phenomena mathematically. It has been found diffusion constant for electrons is different from diffusion constant for holes. It has also been noticed that diffusion constant varies from material to material. Another point before closing to be kept in mind is the ratio of mobility to diffusion constant. It is found a constant. This constant can be shown equal to VT, voltage equivalent of temperature. At room temperature, it turns out to be 26 millivolts. Electronic devices, semiconductors, 8th part, series on semiconductor devices and circuits, lecture number 1.18. The rate of increase of carrier concentration at an arbitrary point in a semiconductor slab is governed by continuity equation. We know well drift current depends upon carrier concentration and diffusion current depends upon concentration gradient, and total current in a semiconductor is sum of drift and diffusion currents. Hence we can understand very easily that the current in semiconductors, it depends upon carrier concentration and concentration gradients, which are governed by continuity equation. This gives an indication regarding the special significance of continuity equation in semiconductor physics. In the present session, the focus is on continuity equation and its applications. Before closing the session, we also consider Boltzmann's relations after continuity equation applications. Now let us move to begin the course session. Continuity equation applications. Under this heading, a prelude to the session is given. Two important applications of continuity equation in semiconductor physics are: one, involves finding variation of carrier concentration with the time when a semiconductor is illuminated uniformly from all directions. A semiconductor slab is there, it is illuminated uniformly from all directions. Consider an arbitrary point inside the semiconductor. When illumination started, electron-hole pairs got being generated. So concentration, electron concentration, hole concentration start increasing. How this concentration varies with the time? That is the subject matter of case 1. In case 2, we try to determine variation of carrier concentration with the distance when a semiconductor is illuminated at one end. In the second case, slab is illuminated at one end, let us say left side end. So only at this end, electron hole pairs, they got generated, concentration increases, and this increase in concentration at one end leads to the existence of concentration gradient in the slab, because at this end more carriers are there, at the other end less number of carriers. So concentration gradient, it leads to diffusion. The carriers start moving towards the other end. While moving, of course, recombination happens, concentration falls. How it falls, how concentration falls along the length of the semiconductor slab, this is the matter to be investigated under case 2. These two cases have certain practical importance and now they are investigated. Now case 1. This situation arises when An open circuited n-type semiconductor bar is illuminated from all sides uniformly. Here we considered n-type semiconductor. It can be p-type also. The results which we are going to get, they are applicable equally to p-type semiconductor bars too. In the present situation, the concentration is independent of X and with zero electric field. What is this? In the analysis, we usually assume the bar lying along x-axis or parallel to x-axis. Bar is illuminated uniformly from all sides. So there is no possibility for the concentration to vary with x. Illumination is uniform with x. So concentration also remains uniform, remains unchanged along with x. So it is independent of x. The situation is with the zero electric field. It is open circuited bar. No voltage is connected across any of its terminals. So electric field, applied electric field is zero. So this situation is one in which dou by dou x is 0 and E is 0. These two conditions, when inserted into the continuity equation, the equation that comes out reads like this: dPn by dt equal to minus Pn minus Pn naught by tau p. dPn by dt means rate of increase of hole concentration in n semiconductor. Pn is hole concentration in n semiconductor. Pn naught is hole concentration in n semiconductor under equilibrium condition. Tau p is lifetime of holes. This differential equation can be solved to get P of t equal to P naught plus P prime of 0 into 1 minus e power minus t plus t prime by tau p. What is P of t? It is a whole concentration at time t. P naught means equilibrium whole concentration. P prime of 0 means whole concentration due to illumination at t equal to 0. Notice whole concentration at a point in the slab, it consists of two components, one due to thermal generation and another due to illumination. P prime denotes that it is due to illumination. P naught means that due to thermal generation. 1 minus e power minus t is time variable. T prime is the instant where illumination is switched on. This equation, it is for the case where illumination is switched on at t equal to t prime and switched off at t equal to 0. Now, P prime of t means whole concentration due to illumination at t is P prime of 0 e power minus t by tau p. P prime of 0 means whole concentration due to illumination at t equal to 0 into e power minus t by tau p. These equations can be understood further deeply. Their physical meaning, implications can be known more deeply if we consider, if we see their meaning in pictures, which is done in the next slide. Here is shown horizontal axis is t, time. Illumination is switched on at t prime. It is switched off at t equal to 0. P naught stands for equilibrium hole concentration. P prime 0. This is P prime 0 here to here. This is P prime 0. Once illumination is removed, notice this concentration which is due to illumination, it is falling. The fall is exponential. When illumination is switched on, concentration is rising. Here we can see it is rising. The rising is also exponential. So illumination on raises the concentration in an exponential manner. Removal of illumination decreases the concentration again in an exponential manner. Here the variation of minority or whole concentration in diffusion with the time due to generation and recombination is illustrated. We see now case 2. This situation arises when an open circuited n-type semiconductor bar is illuminated at one end continuously. In this case, the concentration is independent of time t and with zero electric field, implying dou by dou t is 0 and E is 0. So what does it mean? Here is a bar, it is illuminated here. Now, when illumination is continuous for a quite long period of time, then steady state comes into being and no change with the time happens. So dou by dou t is 0. If you consider concentration somewhere here, initially here the concentration may change with time, but in the steady state there won't be any change with the time. So therefore dou by dou t is 0. And E is also 0 here because we have not connected any voltage source across the slab, so E is 0. Inserting these two conditions into the continuity equation, we get an equation, differential equation, which is d square pn by dx square equal to pn minus pn naught by dp tau p equal to pn minus pn naught by lp square. What is x here? Here it is assumed that the slab is lying along x-axis. Pn is whole concentration in n-type slab at a distance of, let us say, x. At a distance of LP stands for diffusion length, dp is diffusion constant, tau p is lifetime. All these things pertain to holes. This equation can be solved to get a solution. P prime of x is equal to P prime of 0 e power minus x by LP equal to P of x minus P naught. What is this P prime of x? P prime at a distance of x. P prime means whole concentration due to illumination. See, at any point in the slab, whole concentration consists of two components. One due to illumination, another due to thermal generation. Thermal generated one is indicated by P naught. And it is independent of distance. Everywhere it remains the same in the slab. It depends only on temperature. Total P naught plus P prime. These two together are indicated by simply P. This P prime of x is P prime of 0 e power minus x by LP. P prime of 0 means illuminated and whole concentration due to illumination, or whole concentration at the illumination end due to illumination. Another part is also there, thermal part, as far as the concentration, whole concentration is concerned. That part is not considered. That is not part of P prime of 0. P prime of 0 is equal to P of 0 minus P naught. one can have a better understanding if we consider all these things in pictorial form. Here, the variation of minority or whole concentration in diffusion with the distance in the anti-bar is illustrated. See, horizontal axis is distance, it is x. Bar is assumed to be lying like this. Illumination is done here. Now, whole concentration. This is whole concentration due to illumination. Another component of whole concentration is also that is P naught. Both put together is total whole concentration. It is indicated by P. Notice it is falling with the distance like this. Why it is falling? Reason is this. It is illuminated, so electron hole pairs get generated and they diffuse towards the other end. While moving towards the other end, electrons come in contact with the holes. So holes may come in contact with electrons. Recombination happens. So concentration falls. It is quite natural to notice the fall of concentration. Continuity equation tells us that this fall is again exponential. Now, after using continuity equation in analyzing two situations and noting the implications, we move to another practical, real situation where we estimate currents in an open circuited extrinsic slab. Notice here is a slab, it is open circuited slab, it is extrinsic, maybe N type or P type, it doesn't matter. Inside this slab, currents exist. Why currents exist? Reason is inside electrons exist, inside holes exist. Electrons don't keep quiet, holes don't keep quiet, they keep on moving. Electron moving means electron current comes into being. Holes moving means hole current comes into being. Electron movement is associated with the drift and diffusion. So two components. Holes are also associated with the drift and diffusion. Again, two components in them. So point is, even though the slab appears to be calm, quiet from outside, inside it is not so. As long as it is above 0 degree Kelvin, inside a lot of turmoil in which electrons, holes keep on moving in a random haphazard manner, resulting in currents. We try to estimate those currents here, right now. These are useful for us in the derivation of diode equation or Shockley diode equation. Here, an open circuited N-type semiconductor bar under low-level injection conditions is considered to estimate its various current components. An example for low-level injection is when bar is illuminated or irradiated lightly at one end. This situation arises in the functioning of diodes and hence certain special significance. Here we are considering low-level injection. Low-level injection means illuminated lightly at one end. A slab illuminated lightly at one end, which is case 2, which is analyzed just now, coming to this topic. So the results of analysis which we did just now, we are going to use them. They are going to be useful to us. Analysis gives in minority carrier current, the drift component is negligible when compared to diffusion component. Hence, injected minority carrier current under low level injection condition is essentially diffusion current. All the currents fall exponentially with the distance from point of injection. So we do actual estimation here. Diffusion current due to minority hole, IP of X is equal to minus EAdP dou P by dou X. Here the slab is assumed along x-axis. IP means I current in amperes, P due to holes. This is a standard formula for diffusion current due to holes. A is cross-sectional area, E is constant 1.6 into 10 power minus 19, dP is diffusion constant. P is given by this formula. This relation we derived in case 2. So we are using the results of previous analysis. Substituting this in this equation, we get this expression. Diffusion current due to minority holes. Now diffusion current due to majority electrons. Diffusion current due to electrons is given by this formula. In of x is E A dn dn by dx. Of course, for holes, we have this relation. Like electrons, like we have a relation for holes too. Lot of similarity except this minus sign. Now consider the ratio In by Ip. From that, In of x can be found equal to minus dn by dp Ip of x. Ip of x is known to us, dn dp, they are available in mathematical tables. So Ix is known, In of x. Drift current due to majority electron. Earlier slide is about diffusion currents. Now it is drift currents. It is open circuited slab. So therefore, terminal current is 0. This is slab. The current entering or the current leaving is 0 because it is open circuited. Inside the total current, it has 4 components. Sum of these 4 components is terminal current. Therefore, Ip plus In plus Ind plus Ip, it is 0. Ip means diffusion hole current. In means diffusion electron current. Ind means drift electron current. Ipd is drift hole current. Now, Ind is equal to dn by dp minus 1 Ip of x. Field is required. Ind is drift current. Drift phenomena is always associated with potential gradient. Existence of drift current means existence of a field. The field associated with this drift current is, it can be found as equal to 1 by EAN mu n dn by dp minus 1 Ip of x. Drift current due to minority holes. This is the expression for a drift current, hole current. That's why P, mu P E. If you multiply it with the A, cross-sectional area A, then we will be getting current in amperes IPD. So IPD of x is equal to P by N, mu P by mu N, dN by dP minus 1 Ip of x. With this, we are able to determine all the 4 components of currents inside open circuited extrinsic slab. Now we consider certain important relations known as Boltzmann's relations. The Boltzmann's equations are relations connecting carrier concentrations with potential difference between 2 different points in a graded semiconductor bar under equilibrium conditions. Graded means impurity concentration varying with the distance, varying along the length of the semiconductor. Here it may be less, here it may be more, here it may be much more. The variation of carrier concentration with the length is important property of semiconductor bar. Here is a graded semiconductor A. P1 is concentration at x1, P2 is concentration at x2, V1 is potential at x1, V2 is potential at x2. This is the bar, semiconductor bar, whereas this one is a diode, P-type, N-type, Na, concentration of P-type impurities, Nd, concentration of N-type impurities. And with respect to these diagrams, let us see Boltzmann's relations. According to these equations, in a in semiconductors with the non-uniform doping concentration. That is, in graded semiconductors, the hole or free electron concentrations are related by this formula. This is hole concentration, P1, P2. P1 equal to P2 e power V21 by Vt. N1 is N2 e power minus V21 by Vt. In case of open circuited diode, these relations become Pp naught equal to P n naught e power V naught by Vt, n naught equal to n P naught e power V naught by Vt. In case of an open circuited semiconductor slab, no single hole electron is entering or leaving the slab. Hence, the net hole current as well as net electron current both are zeros. Considering hole current, this is the relation. Current density due to holes is, this is a drift current, this is a diffusion current. From this, E can be solved, and a little bit of manipulation leads us E equal to minus dV by dx. From this, dV equal to minus Vt dP by P. Performing integration leads us to give P1 equal to P2 e power V21 by Vt. So this is a derivation, small derivation pertaining to Boltzmann's relations. Now here a summary of important relations that are discussed in semiconductor physics. They are given here: mass action law, average diffusion length, Einstein relation, conductivity, mobility, Fermi-Dirac function, free electron concentration, hole concentration. These are all important relations we come across several times. Forbidden energy gap, Fermi level in intrinsic semiconductor, Fermi level in n-type semiconductor, Fermi level in p-type semiconductor, Boltzmann's relation. With this, we come to an end to the present session. Before closing down, let us recollect important aspects. It is mainly about applications of continuity equation. And then we considered Boltzmann relations. Hope this session is useful to you. We meet again in another session with a new topic soon.